we have demonstrated, or we have arrived at the Navier-Stokes equation, and we have shown it in vector form as well as in components form in x, y, z, the rectangular coordinates, as well as in cylindrical polar coordinates r, theta, z. And now, before we start trying to solving a problem, we need to consider also that what are the other things that we need to, number one, to solve, and also number two, to make note of them, or to always keep in mind what are the essentials of solutions of Navier-Stokes equations. So two types of problems that differential equation that we occur and that are important, and they are continuity and Navier-Stokes equation, of course, and from which we need to calculate the pressure and the velocity. If we find the pressure as well as the velocity, or three components of the velocity, then to a reasonable extent we can explain the fluid flow behavior in x, y, z or r, theta, z directions. So calculating both of them, they are attached to each other, they are coupled with each other, and they are also related to the geometry in which the particular flow is taking place. It can be a fluid flow in an open channel flow, like in a river, in a canal, etc., or in a cylinder, pipe, and that kind of thing. So these are important considerations that we take note of that. And the variables that are unknown are, as I said, pressure and the velocity, three components of velocity, and then of course there is pressure. And to solve them, we have these equations available to us. We have the continuity equation, extremely useful when it is incompressible fluid, and you can see that the other terms have gone. The time dependent term is gone, and there is no rho appearing here. So it's simple, divergence of V equal to 0 in the vector form. And in the vector form, you can see here that we have derivative of V, of course, appearing here, which really gives us the material derivative of velocity with respect to time, and this equates all the other forces that are acting on the fluid. So this equation itself shows that the Newton's law of motion, F is equal to ma, is being applied and is being followed. So these are the equations available to it. These are the unknowns that we would need to determine to be able to explain the fluid flow. And we need to consider at times the boundary conditions also that are being applied in the fluid flow. Boundary conditions play an important role for solution of Navier-Stokes equations. Without that, in fact, things are not complete, because a real flow always takes place in a certain boundary. And so the relationship between the velocity and the pressure is very close. They are interrelated with each other. The pressure difference gives rise to a motion. It can have viscous effects as well. It will give rise to the viscosity, the resistance, and the shear forces that appear in the equations, and so on. But for considering a particular conditions that are there, we need to find out the solution. And therefore, while solving these equations, these are the few things that we have to take into consideration.